Good evening, our ESSEC alumni and students, as well as our partners of the school. My name is Ian Ong, and I am the Alumni Relations Manager for ESSEC Business School. I'd like to welcome you to our first ever hybrid event here at the Asia Pacific campus titled The New Way for the Semiconductor Industry, Challenges and Opportunities. Thank you for taking the time out for your busy schedules to attend this event here in the campus, as well as online via Zoom. I would now like to start the event by asking Liu Tan, the Associate Director of Career Services, Alumni, and Corporate Relations, to say a few words. Liu, please.
Hi, good evening, everyone. Thanks for coming down and joining us in this first hybrid event. You know, it's also new for me. Both we have friends online joining us and all of you here in the campus. I'd just like to say a few words. I mean, I myself, I come from semiconductor industry, so it's a topic very close to my heart. And we all know, right, semiconductor is something that we can't live without, literally. Of course, I'll let our guest speaker, elaborate a bit more. So I think we have seen that the past few years, the pandemic has really accelerated the demand, and we have global issues, rising from supply chain disruptions and many other things. But this is a very interesting and yet complicated industry with lots of value. So I hope that today's session, it will bring you a lot more awareness and knowledge, because traditionally it is a B2B industry, right? So maybe for the layman, the understanding of its impact might not be as aware. So I hope today's session will be something meaningful for all of you. And without further ado, I'll hand you over back to Ian. Thank you so much.
Thank you.
Thank you, Liu. I would now like to invite our event's main speaker, Francois Guibert, for his presentation. Francois is a former Greater China and South Asia president at STMicroelectronics. He will now be presenting on the following topics: introduction to semiconductors and the electronics and semiconductor industry story. Francois, over to you.
Thank you.
So the title is speaking by itself, the intelligent skill of the 21st century, and you will see why, and going beyond imagination, because 80 years ago, 75 years ago, we didn't know that semiconductor would be so crucial for most of the other industry as it is today. In fact, this industry is quite young in some way, but because it was B2B, it was not so much recognized by even the educated public. So let's go one by one to give you a picture of this semiconductor industry. We'll go to the detail on how we design, how we manufacture, what are the positioning of this industry, in particular within the electronic business, and what is its history of development, which is also quite unknown. So let's start by the beginning. We have to go a little bit technical, because this industry is based on semiconductor, and I want to explain what is semiconductor, because there are basically three kinds of material in the world. The one, insulators, that doesn't conduct electrical current under normal condition. It's rubber, plastic, glass, mica, quartz. The one which are conductors, and you know them as well. They are easily conducting the current: copper, silver, gold, aluminum, and so on. And you have the one which are in between. In fact, there are materials that are between conductors and insulators, and has the ability to conduct electrical current under some application of voltage. And silicon is one of the most representative within arsenic, boron, polonium, germanium, and tellurium. The reason why it's semiconductor is because at here, when you look at the detail of the silicon atomic structure, you have a few electrons that are ready, let's say, to get a little bit out of the power of the nucleus and start to, let's say, move from one atom to another atom and provide current with electrons moving or lack of electrons, that means holes. So, in other words, indeed, you have something between insulator and conductor that you can control. Now, the transistor, which is at the basic of the semiconductor industry, is based on the fact that within the silicon, you can create zone of emitter, collector, and base, or sometimes called drain, collector, and you have area which has been doped by introduction of impurity, which is a trivalent or pentavalent, and which allow to even accelerate the transfer of electron or holes from one side to the other side. In other words, you will have a current between these two sides, between the emitter and the collector under the base control. In other words, it's a switch. If you have, let's say, current, you have 1. If you have no current, you have 0, you have no current. And but you can use it also in different ways. You can use it in analog. That means you can open a little bit the current, and you have, let's say, a certain level of current that you can even amplify, in particular in the what we call the bipolar junction transistor, which will, in fact, capitalize on the hole and the electrons to make, let's say, a real amplification of the current itself. But most of the time, it is used as a digital 0 to 1. And why it is important? Because indeed, most of the calculation for those who have been doing Boolean algebra will be based between 0 and 1. So in fact, whatever semiconductor you have in your PC, in your phone, and so on, they are still doing only 0 and 1. And, but you know, from the basic CMOS transistor, you can do some typical functions, the NAND, the NOR, the AND, and the OR. And when you combine them in a lot of configuration, you end up by doing a lot of addition, multiplication, and very sophisticated mathematical function. So you place this function in memory in your CAD tools, and you can call them upon, let's say, your request to make any kind of functionality, having in memory the one which are already developed and that you want to easily integrate in your design. And therefore, if you want to do, for example, the decoder for TV, which is a very complex function, where you have to compress and decompress the images when it is sent by cable or satellite, you will have a real, let's say, complex functionality of decoding of images, of processor, of memories, of display, and so on for the graphics. So it's a very highly complex function, and you have really inside 1 billion of transistors. From the tape generated on the design, what we call PG tape, pattern generated tapes, you send it to specialists, special companies, which are doing the set of masks that will allow you to translate this design on the silicon. And we will go later on that. So this is a design activity. It's very complex and requires a lot of capability of using the mathematical function to really perform a very complex calculation. Now, all the magic is to translate this design through the mask to the silicon on the wafers, and then to the finished product, which is the package that you can see here on the top. And to do so, first of all, you need to have the silicon. The silicon is made basically from sand, or from even, you can find it in the rocks of some, on Earth, it's very easy. It's a very, let's say, easy natural resources. And there is a lot of capability to really have this silica sand. Then you treat it thermically and mechanically and do an ingot of silicon, which is this big area here, and you extend it basically on 10 or 20 meters to be sure that later on you can slice it and you have the basic wafer. Then, of course, you have to put the design on these wafers, which is what we call the front end, on the lot of steps that I will display later on. Then you end up by this finished wafer where you have each individual chip which has been duplicated, and you will slice them, each of them, put it in a lead frame, and so on, and you end up by this product. So let's go one by one on the front end first. The front end is a little bit like the photography. You have a negative with the mask, and you need to do a 2D, but a kind of 3D dimension projection. And we are using, in fact, laser with deep UV or even extreme UV wavelength to be sure that on a photoresist that has been put on the silicon, you can start to really incrustate, make the incrustation of the transistor and define the different area to be sure that at the end you have a full transistor with the emitter, the collector, and the gate. So this is very complex because you work at nanometers, 10, 7, even 3 in the most updated one. So between these two machines, some of these machines here are typically, let's say, in the range of $30 to $70 million each. And some of the most advanced for the 3 nanometers will cost you $140 million. So for one equipment. Then you have the etching, you have here a little bit of detail between the photoresist, you have the exposure, so the laser put, let's say, here, define what you have to do. And in fact, you have the development, the etching with this machine, and then you end up by having, you see, the emitter, the collector, and later on you are going to put the gate. In fact, we'll do in between some ion implantation to make it even more efficient, to be sure that you maximize the level of number of electrons or holes that are going to be the current for the 1 and for the 0. Some diffusion to make it even more performant. And then you will go to thin metal deposition, and then you will start again the same process. So this process is repeated almost 100 times to be sure that, and there is many metal layers to be sure that you can have, and you have connection, what we call via, to connect each of these transistors basically a burger. You have many levels, and you can, it's very thin, let's say, burger. So you can really have a superposition of transistors that are all connected to each other to perform the functionality that you are looking for. Then you have to polarize, because with all what you have done start to be a little bit bumpy. Then you have to make it the back also to be, let's say, as thin as possible. So you are making the wafer back grinding, and then finally the wafer testing. That's what we call the front end. It's the most difficult, the most strategic part of the manufacturing. But the backend operation has also very strategic importance, because you have later on, I wanted to show you the complexity of a manufacturing location. And you can see that's a typical set of machines, whatever, of course, served sometimes by robots, not all of them. Sometimes there is also people inside, but it's very automatized, and you have all this machinery of furnaces, of etching machine, of photolithography, really on a building which is very clean, because since you are doing things at a few tenths of nanometers, your hair on one of the chip will destroy completely the functionality. And therefore, we have to have a defect density of the fab, which is not having, one particle of 0.1 micron in 1 meter cube. So this is very sensitive. Therefore, that's the reason why, if you were having a surgery in a clean room in semiconductor, you will be very safe. There is absolutely no pollution. So, the backend is also key. You have to really make the wafer dicing of each of the different components which has been duplicated on the wafer. You have to put it on a lead frame here, and you have to make the bonding. So why bonding is a very interesting to see. You have a machine which is, let's say, making the bonding between the output of the circuit to the lead frame for the connection here that you can see here. And they can do 360 connections like that in 1 second. So when you see the speed of the machine, it's extremely impressive. That's the part of the backend that I have always enjoyed the most, to see the ability of manufacturing tools to make, let's say, wire bonding at a speed which you cannot believe. Then, of course, we have to protect this die inside the package with some resin molding, and then you end up by the final product for the final test and the shipping. So you have seen the 3 major steps: the conception of the design, the front-end manufacturing. If you meet with people in semiconductors, they will know very well what you say, which is front-end or back-end. It's two, and also the testing. The testing is very complex now. So this is where, and this is some also back-end operation, and you can see the bonding here. It should have been even better in a movie, but I have only the picture. But it will be very impressive to see the bonding of semiconductor chip. Now, what do we do with this chip? We put it with other chip on a board, and this creates basically the electronic system. Here, I took the example of a cellular phone, where there is the usual baseband processing, audio speech processing, application processor, the speaker, the micro, the camera. You have basically used the architecture of a cellular phone. But if you look at the phone, you have the impression that you buy a phone, but you buy basically semiconductor inside. On the hardware standpoint, the manufacturing cost is based on cost of chips. There is a few, the glass, metallization, and so on. But a phone is basically today full of semiconductor, 85% basically of the manufacturing cost. Now, of course, there is application and there is operating system, which is millions of lines of software. But on a pure hardware standpoint, the semiconductor is at the core of it. So let's look at the way it developed, because I'm talking about the today. But you know, we didn't start like that. We started in 1947 by the first transistor. And here you can see that you have the emitter, the collector, and the base, which is with the power, with the voltage. And this was done at the Bell Laboratories by William Shockley, and also one other associate. And it was 4.6 centimeters squared, the first transistor, 1947. Then in 1958, Texas Instruments, Jack Kilby, created the first combination of transistors. You can see that it's still quite not so high-tech on our point of view today. But it was the first combination of a few transistors inside that was making some more sophisticated functionalities than just a transistor. And then the revolution came in 1971 with the Intel first microprocessor. Everybody knows Intel. In fact, it's the only one which is well known by the public, because it is on all your PCs, there is something saying Intel inside. That was their best communication program for almost 40 years. And then there was memory, which started to be gigantic, the 4 gigabit DRAM, and then some processor also, and so on. And in 2021, IBM, who is not doing any more volume manufacturing of semiconductor anymore, but is still doing a lot of R&D in the high-tech area for computers and semiconductor, has been setting up a 2 nanometer test chip with 50 billion transistors. And reading the document, I was amazed to see that it was also on 4.6 centimeters squared. I think that they did it on purpose, because this one was 4.6 centimeters squared. So one chip, 50 billion chip on the same area. That's what I call a big change in an industry in less than 70 years. Now, why this race of the technology? Why do we do that, and for what are we looking for? Well, I took an example of a phone. This one is the first cellular phone of Motorola in 1983. It was 10 hours to charge it. You can speak 30 minutes. It was weighing 1.1 kilo. It was costing $4,000, which is $10,000 today, the price of a car. And you can do phone call only in US and only phone call. Today you have I took the Xiaomi one, the 3 hours for charging, 35 hours of talking, less than 200 grams, cost, let's say, around $100 US, and you can do all of that. Phone call, camera, photo gallery, internet connectivity, GPS, audio, music, video, games, whatever you can even dream about. That's a big change. And as you can see, the phone is even 3 times smaller and 10 times weighing less. So they sold this one in 1983, 1,500 pieces. In 1984, 7,000. In 1985, 10,000 pieces worldwide. This one is this kind of phone today by all the manufacturers is 1.5 billion per year. That makes also a big difference. So 1983, 2020, 21, you can see that within basically 40 years, we've been doing tremendous progress on the way you can use semiconductor to perform functionality, which is at in the palm of your hand. Now, indeed, why the volume has been changing? The volume was, and that's the reason why maybe until 2000 it was not so evident to see the chips. It was mainly used in mainframe computer and switching system in the 1960s and 70s. The big switching system for your phone, the phone at home, not your cellular phone, for digital switch. And it was used for mainframe computer. Then in the 1970s, it was analog TV, office equipment, fax, copy machine, CRT monitors, the big one, if you remember, with the big video. And then moved to the printers, the laptops, the automotive, the network, and so on, and finally the cell phone. At the same time, the basic unit per year was here 1 million, and here now 1 billion. So that was really a fantastic growth in volume for basically the application, the different applications that was emerging gradually from the electronic business. And then, of course, now the prepaid telecom cards, the smart device, the wearables is always in billion, and the IoT is even in billion of pieces. So almost a new application is addressing hundreds of millions, if not billion of, let's say, consumer devices. Now, there is, the semiconductor has a second capability, not only to increase in volume because of the demand of the electronic system, but also by the pervasiveness of the semiconductor in the same application to become more and more significant, and also to go to many other applications. As I was telling you at the beginning, it was mainframe computer and switching system and so on. Then it went to TV, to automotive, to phone, to PCs and so on. But within the TV, the semiconductor was 5%, today is 70%. In a car, in the 70s, it was 0.1%, a few dollars under your hood. Today, with the regular car, the hybrid car, the electrical car, you can go up to $1,500 of chips inside the car. That's a big. So if you were doing even the same number of cars as in 1970, the semiconductor industry is selling 1,500 and not $1. That's a big change in terms of volume requirement. Same for the PC. You remember maybe, no, you are young, maybe not all of you remember this one, but you remember the phone. The same even for your washing machine, dryer machine, washing machine, whatever. So semiconductor pervasiveness is such that not only it goes to many new applications, but it goes also in large volume to increase in size the same application. Now, how did we go from, I took the example of two computers. This one is ENIAC computers in the US. It was done with vacuum tube. It was having 17,000 vacuum tube and was capable of doing 5,000 addition and 300 multiplication in 1 second. This one is the latest IBM Q system quantum computer, which is doing million of billion operations in 1 second also. So how did we go from here to here? Let me show you the story. Story started in the 1950s with USA for the computer defense and then the semiconductor. You will see that the driving of the semiconductor was the electronic system. The first launching of strategic program was on electronics, and then the semiconductor followed. It has been always like that since 60, 70 years. Europe tried, let's say, to compete on the computer, but failed. But unfortunately, came back later on telecom. But in between, there was Japan, which started also in the 1960s, 70s, then followed by Europe in telecom. And then in the 1980s and 1990s, Korea, Taiwan, Singapore started almost at the same time, and followed by China later on, basically the year 2000. And there is many other block of countries or big, let's say, countries that can also, let's say, be part of this development, like India, Asia, and Latin America, which are not still having, let's say, semiconductor industry very present in their country, but potentially they are huge potential. Remember that in year 2000, ASEAN will be 700 million people, including, of course, Singapore. Latin America is already 550 million, and India is already also 1.3, 1.4 billion people. So at a certain point of time, they will have also to do some local, let's say, activities on design, on electronics, on many areas. In particular, with the strategic of independence that everybody now is looking for. So let's go one by one, because it's very important. 1950s, just after war, the space and defense. You remember that the space and defense was basically funding the R&D at the NASA, at the electronic manufacturer, and so on. And they started to really have two kinds of development for the equipment itself, for military and space in particular, and of course started to develop the components in the 1950s. Then in the 1970s, the Silicon Valley started to appear on the map. And really, it was a kind of fantastic idea to melt inside the same almost area, the hardware, the software, the people from the electronic system, from the semiconductor, from the R&D laboratories, universities, everything inside. And that created the success of Silicon Valley, in particular in the 1980s and 90s, and remains still very, let's say, powerful. And obviously at the time, America was leaders in software, in mobile, in data center, in semiconductor, in almost everything. But today I split it in 3 areas. The one of PC and software, Dell, HP, Apple, IBM, Microsoft. The one of data communication and social networking. You know these words and these names, sorry, much more than me, because you are using them a lot. And obviously, maybe less this one, except Intel, maybe NVIDIA, which is starting to be very well known now by the business community. But you know, Texas Instruments, Micron, Analog Device, EMBA, Broadcom, Qualcomm, all the top, let's say, players in this industry. So, US has a full ecosystem and was at the origin of this development. And that was why in semiconductor we all speak American. So Europe was a bit more complicated, but quite successful. We started to compete on the computer, but as I say, ICL from UK, Siemens from Germany, and Bull never succeeded to compete with IBM. And hopefully, the telecom industry started to be successful in the 1970s in Europe. You may remember the key players like Nokia. I would like to say that Nokia in the year 2000 was having 40% of the cellular phone market. Ericsson, Siemens, Alcatel, Thomson Telecom, there was a huge variety, and in fact, Europe was really having a very strong footprint on the high-tech industry worldwide. Then there was the European Commission started to have some national program to develop product for this telecom industry, and started also, like the American with the space and defense contract, started to fund the development of technologies and product for this marketplace with some program that was called Esprit, Eureka, Jessie, Medea, and so on. And Europe became quite leader in the automotive, the telecommunication, the smart car industry, which was, by the way, invented in France, the opposite of sometimes what I read, but I can tell you that it was done in France. And then 3 leaders appear on the roadmap. Well, they are called today ST, Infineon, and NXP, but this one is a joint venture between 2 companies, SGS and Thomson, which was French and Italian. Infineon was Siemens Semiconductor, and NXP was Philips Semiconductor. So the names are new, but the history is coming from this big company at the time. So Europe did succeed, and let's look at Japan. Japan has a long also history because they started in the 1960s with the radios, the audio cassette. Some of you may remember this small audio cassette, which is known now sometime, but it was basically the only music that you can record and listen easily in the 1970s. And then Japan made a fantastic giant step by establishing the VHS standard on the video recording. At the time, the video recording was costing almost 2,000 US dollars, and was a machine which was weighing basically 10 or 12 kilo, the video recording. I remember because I got one, and believe me, it was on the table, it was really taking the space. So, but they won against the European and the American standard, and the VHS became the videotape of the following 10 years. So at the time in the 1990s, the semiconductor also was well established with a lot of players from Japan. I am mentioning here just a few of them. But I can tell you I was in US at the time, in 1983, 84, 85, myself, 86. And in the top 10 semiconductor players at the time, 5 in the top, even in the top 5, 4 was Japanese. And you see Toshiba, Fujitsu, Hitachi, Mitsubishi were very strong players, in particular in the memory business, on the DRAM, on the static RAM, and later on, of course, on the flash and so on. So Japan established its leadership in digital consumer, in robotics, and in semiconductor. However, Japan closed a little bit the door to the open space of development of the high tech, and remain between Japanese, merged between even Japanese companies, and they have reduced a little bit their footprint. There are still some key leaders, but in particular in the digital consumer, in the robotics, but in semiconductor, 2 of them remain very strong, but there was much more before. And therefore, the footprint of Japan has a little bit reduced. Remember that the GDP of Japan grew only 0.2% for 25 years, from the 1990 to year basically 2015. So that was Japan, which is still a very powerful country with Toshiba and Renesas. Renesas is in fact the combination of Hitachi, Mitsubishi, and NEC. semiconductor. Now, let's move to Korea. Korea, like Japan exploited the Kairatsu concept, Korean have the chaebol concept. The same concept, but really, let's say, extremely efficient in the way that, you know, in the chaebol, you have everything. You take Samsung, you take LG, and you have banks, consumer electronics, semiconductor manufacturing, distribution network, and many other things. In fact, I live in Korea for 6 months, and I can tell you, even my suit was coming from Samsung. Of course, the brand name was different, but the guy selling it to me, he said, I don't know the brand, he told me it's from Samsung. So they are doing so many things, but really they became leaders. So both Samsung and SK hynix, which was Hyundai Group before, become an LG in consumer. So semiconductor, mobile phone, and consumer became the cup of tea of Korean, and you know how strong they are in that area. Now, Taiwan was a different model, but still very successful. Taiwan started by doing a lot of manufacturing at the time for even audio and toys and for the PC motherboard, for, of course, the big American company. And but later on, started to do the PCs themselves. So they have a huge already story on key manufacturing for the American company. And then the government created an agency called E3 for the electronic business, and even a subsidiary of the E3 called ERSO, which was specialized for developing the industry of semiconductor in Taiwan. And they started to create Hsinchu, a little bit like the model of Silicon Valley. And you know, the Taiwanese, they were so close to Intel that they have seen that the leadership was coming from the technology. So they started in Hsinchu to develop UMC, TSMC, and not only to be good in manufacturing, but also to be good in the technology. And you know very well that today TSMC is almost 60% of the total silicon foundry, and UMC is a good player also, quite smaller, but still. And MediaTek is a good also design house for, in particular, decoders and graphics and so on. So strong leadership, both in the PC and in the semiconductor foundry business. Singapore is a very special case because there is no big leader today. There were companies that were started, Chartered Semiconductor, in the 1980s also, at the same time than the others. Temasek was a key, let's say, holder of Chartered Semiconductor, but then Chartered didn't succeed and was acquired by the year 2000 by Global Foundries. And therefore, there is no leader. It's difficult for Singapore. There is no internal market to really start, you know, to capitalize on the application, to have volume manufacturing internally in the same country. Korea, Taiwan, and US and Europe has this capability. So what they did, as usual, very well, is to become the international manufacturing hub for most of the key players worldwide. Therefore, you have in Singapore front-end, you know what is front-end now, that means manufacturing of the wafer silicon with the design inside. So Micron, STMicroelectronics, Infineon, Global Foundries, UMC, SSMC, VIS, Vanguard, International, which are Taiwanese and so on, are there. And even on some back-end operation, which are, this one is Taiwanese, this one is Singaporean, and this one is Chinese. So a lot of companies in the small island of the red dot, as Singaporeans sometimes also call it, has been mushrooming in Singapore in the last almost 50 years and become extremely successful. Indeed, if you look at the electronic cluster that EDB is publishing every quarter, you can see that the electronic cluster is 70,000 people and 33,000 are employed in the semiconductor. more than half of it are working in the semiconductor industry itself. And it's one of the largest manufacturing industry cluster. It represents 20% of the total R&D expenditure in Singapore and create thousands of jobs for workers and technicians and engineers. I will come back on that later on, I believe, in the Q&A session. But this is key. We need human resources. We need not only workers and engineers and technicians, we need also a lot of people for business, in sales, in marketing, in accounting, in audit, in treasury, in procurement, in everything. So I encourage all the business school to also look at a good career in semiconductor. And China has, of course, the power of the 1.4 billion. And we have them that started quite late in the year 2000. But in 20 years, they become also mostly the electronic manufacturer of the world. I say electronics, not semiconductor. People have a tendency to believe that since everything, the cellular phones, the computers are done in China, they do also the video. They do, but they are very small in semiconductor. But indeed, depending on the application, TV, PC, cellular phone, it can be between 35 to 70% of the worldwide consumption of electronic application. But the one of semiconductor was small compared to what they do in the electronic overall. Now, if I look at all this, what are the ingredients of success? The ingredient of success in the past 70 years has been, people have been trying generally to focus on one application in the country. The PC for Taiwan, the consumer for Korea and Japan, the telecom for Europe, and the space and defense and many others, and all the, basically the industry in US by history. But they need a kind of ecosystem. They need to have government focus, a good education system, incentive, because it's a very capital and very costly, even R&D resources requirement for semiconductor, and also the key part of the technology park. This is key because this is where coming innovation, the mushrooming of ideas and innovation, like in Silicon Valley, in Sichu, but also, you know, in Suwon, in Korea, in Osaka, in Japan, and so on. There is plenty of spaces which are basically technology park, not only Silicon Valley. You have to have strong R&D effort. It can be some government funding or financial and industrial players. It can be some entrepreneur dedication, development of startup, mostly in the US, the diversification of major industrial group, like in Taiwan. You know, the Taiwanese company are generally coming from most of those, not TSMC and so on, but most of those players, small one, has been basically the subsidiaries of big companies that were doing container and cables and machinery and so on. It was really the diversification of big groups. And the partnership between electronic and semiconductor. And they become successful in electronics, and the semiconductor will reinforce this ability to develop product in consumer, in telecom, in computers and so on, which are more and more sophisticated, performing well, and therefore it's a very virtuous circle that has been put in place. I have a copyright on this chart, but it's very important when you talk to countries or block of countries, if they want to enter in this business, this is the way, the ingredient of success of the players before. And I will end up this part, hopefully on time, with this chart. There is, most of these people are unknown to the industry. But you know, I put the, first of all, it is my chart. So it is the one I found, I put the one that I am very close to, or I have been the chance to meet. But here, of course, are the pioneer and the founder, the William Shockley and Jack Kilby. Both of them are Nobel Prize at different time. You have on the other side, Andrew Grove and Gordon Moore, the famous Moore law that I'm sure all of you are aware of. And which has been at the core of the Intel company. And the two in the middle are, let's say, very key for me. Mr. Pascal Pistorio was the CEO of STMicroelectronics for 18 years, from 1987 to 2005, and has been merging two companies, which are almost the only successful merger of equals at the same parity of two European companies, French and Italian, and Maurice Chan, who has been also even the one that really not only set up the Hsinchu, because he was the president of E3 and ERSO, but also, of course, he was the CEO and chairman of TSMC. So you have some names which are, for me, very familiar, and you can see that there is still a very, let's say, famous pioneer, and people has been following carefully this industry to still become very strategic, and we will see later on the new wave application and the positioning of the semiconductor players in the next session. Thank you very much.
Thank you for the presentation, Francois. We shall now take a break for dinner. For those who are attending here in campus, kindly adjourn to study area 2, located at level 5 for your meal. And for those who are attending online via Zoom, I hope you have a great dinner. And look forward to see lunch. Lunch or dinner. Okay, and look forward to see you back at 8 p.m. Singapore time. Thank you.
Lost in your mind, I wanna know, am I losing my mind? Never let me go. If this night is not forever, at least we are together. I know I'm not alone. I know I'm not alone. Anywhere, whenever, apart but still together. I know I'm not alone. I know I'm not alone. I know I'm not alone. Unconscious mind, I'm wide awake. Wanna feel one last time. Take my pain away. If this night is not forever, at least we are together. I know I'm not alone. I know I'm not alone. Anywhere, whenever, apart but still together. I know I'm not alone. I know I'm not alone.
Welcome back, everyone. Without further ado, we shall now continue with Francois' presentation on the following topics: the new wave of semiconductor markets and applications, as well as the positioning and challenges of the top 20 players. Francois, please.
Thank you. So let's go quickly to the big change in the semiconductor industry, in particular in the year basically 2000. we move from indeed supplying industrial need, as you have seen at the beginning, big mainframe computer, office equipment, and so on, to in fact answering society calls. That was really what the main changes that happened between the 1919 and year 2000, when we are addressing the high volume and the volatility also of the market to the big consumer, grand public. So what means for me the consumer needs, consumer call, climate change, health and wellness, connectivity and application, Industry 4.0, and safety and protection. That's what I call a kind of an executive summary of the requirement of the, in particular, the new generation and the consumer today. How do we address it? With green electronics, with biomedical, Internet of Things, robotics and automation, and advanced security. And how is it deployed? Low energy, enhancing life, apps and platform, and of course, speed, portability, globalization, mobility. In other words, focusing from the consumer call, society call, to really something which is achievable within the semiconductor industry. So I will go one by one. First, green electronics. There is plenty of things that you can do on CO2 reduction, renewable, CO2, no toxic material, and so on. We are doing it, first of all, internally in the semiconductor industry itself, but we are doing it also for energy harvesting, in particular for the solar cells, the windmill, and many other applications. The green, all the green appliances. You know, the green appliances, in some way, you remember the TV. The TV in standby mode was very high consumption of power. Today, the consumption of your TV in power is still, of course, a bit, but you know, is 100 times less than it was 25 years ago. And the green vehicle, of course, I will come back on this one. The smart grid. The smart grid is basically this smart metering system that allows a power company like Singapore Power, you know, to have directly access to your consumption, tell you if you are consuming during the night, during the peak, or the very low cost, let's say, period of supplying energy and so on. So the smart metering, but smart metering is full of semiconductor. And it's in place now in many countries, in Europe, in China, in Singapore, and in the US. So a lot of things can be done through semiconductor on the green electronics. And the most visible is, of course, in automotive. In automotive, the semiconductor consumption, what we call the TAM, the total available market, has been in 2020 close to 30 billion. And it's going to continue to grow at 15.6% to reach in 2023, 45 billion. This is a big change in the semiconductor value in this automotive business. Why? Because not only, of course, moving from regular engine to hybrid and to electrical, but also having, let's say, a lot of what we call ADAS, Advanced Driver Assistance System, which allow, let's say, the driver to have a lot of safety and security and positioning and access to a lot of connectivity that was unknown even a few years ago. So the car, instead of having a few dollars, then a few $100s, will be very soon a few $1,000s in the coming 5, 10, 15 years. Of course, depending on the model and the low end, middle end, and high end. So automotive will remain a very strong driver of the semiconductor more and more. The semiconductor content, as I was showing you, could be close to 15%, you know, of the cost of manufacturing car. Now, the healthcare and wellness is, of course, key. I will go a little bit in detail, but you know, we have 3 major challenges: the increasing aging population, and Singapore is well placed in it. The increasing epidemic and pandemic risk, I will not talk about that, everybody knows, but also the increasing lifestyle and full related illnesses. So there is plenty of things that can be done with semiconductor on the global challenge, So we'll go one by one on healthcare, on diagnosis, prevention and monitoring and therapy very quickly. On the treatment, you know, we can do a lot. There is 3D printing of custom-made prosthetics. You have a printing tissue and organoids. You have robotic for surgical. You know, 20–30% almost of the surgery done in US are done with robots. And this is making a big improvement also. The radiology, the surgery preparation and so on. So in other words, the medical, which was not even a business 20 years ago, is becoming now a fast-growing business for the semiconductor. And on the diagnosis, you know, this is, for example, you know, all what it is a PCR in 5 tests. You know, you can do it on a semiconductor. You put it at the entry, you have a PCR, let's say, test area, which is done by inside, let's say, even the chip, and you go to detecting, let's say, any kind of disease. It can be, of course, for COVID, but it can be done for dengue, it can be done for many other, you can do 100 almost tropical diseases, check. So the same on remote monitoring. You can have really, you can have sensors, you know, that, for example, for all people, and when there is not too many retirement homes in some countries, you can have sensors that will let the people know very quickly if your grandfather, you know, is just lying on the sofa nicely, or is having a heart attack and is falling, let's say, on the floor. That will be the way also to really intervene very quickly with a medical call and so on. Of course, it's a full ecosystem that you need to have, but the semiconductor will allow to do that technically. And you are a young student and so on, so I will not, I have to mention what you know very well, the lifestyle and wellness and all, you know, the sensors that you have around you when you are doing jogging and gym and so on, where you can have everything, your pulse, your blood pressure, your speed, the number of steps that you have done, everything. And this is done with semiconductor. There is nothing else except maybe the plastic around. So, very important. Now we move to the Internet of Things. And the Internet of Things is quite simple in some way, but require a few key ingredients. You have sensors to detect, you know, if the proximity, the speed, the acceleration, the positioning, any kind of the light, the temperature, the whatever. And you need to have some data processing, so generally microcontrollers. Microcontrollers are different than microprocessors. Microcontrollers have inside all the, let's say, elements in the chip to make all the calculation, to memorize, to address, to transfer, and so on. Processor really process. It's very dedicated to that. And then use external memories and so on to have the full function. And then you have to have user interface, of course, and some connectivity. And what do we do with that? We can do a lot. At the beginning, you know, it was for lighting, for thermostats, smoke detectors, and so on. But today, you can do everything. If you have an apartment, you know, in the south of the country, in Germany, you can, let's say, have your camera, which is basically a video camera, done in semiconductor, have a view of, let's say, of what's happening inside. You can open the window, you can open the light, you can close the door, you can do almost everything from Singapore. So this is fantastic. And then the Industry 4.0. Indeed, all the manufacturing, including for many, not only the electronic business itself, but for automotive, for pharmacy, for many industry, is starting to be very intensive and using robotics. You know, the one who has been doing vaccine, you know, in the past 2 years, instead of doing a few 100 million, they have to do billion of vaccine. And therefore, you need to have a manufacturing at the level of the requirement of the society and so on, which require a lot of automation and therefore robotics. So you can see from the simple robotics to clean, of course, your apartment, which is very easy, of course. You can have manufacturing, you can have medical surgery, pharmaceutical, automotive, and all these robots, of course, have a lot of software and some also mechanics. But you know, the core of it is full of semiconductor inside. Microcontrollers, sensors, and obviously interface, Wi-Fi, and so on. So, if you look at the last one, the safety and protection, this is a data center. And the data center is basically only semiconductor. You open one of his drawers here, you will find memories, processors, and some power devices to be sure that it is not warming too much. And it can handle, let's say, the energy required to make it working smartly. So people may feel that a data center is a data center, but it's only semiconductor inside. So I want you to really keep in mind that indeed the semiconductor is everywhere and spreading everywhere, even more and more every year for the coming years. So let's move to the positioning and challenges of the top 20 players, because you have to, first of all, let's look at the business model. There is three kinds of category. The one doing just design, what we call the fabless. So they do the conception, as I was showing you before. They do really the design of very complex, generally, function. So NVIDIA, Qualcomm, Broadcom, AMD, MediaTek. You have the country of origin in the different color below. Then you have the IDM, the one doing everything. They do the design, the front end, the back end, everything, and they sell the product directly to the end customer. And you have the foundries, which is doing only the front end. Don't do the design, they don't do the back end, they do just, of course, the front end is the most capital intensive and delicate, smart manufacturing part of it. So you can look at it the other way in terms of the 20 leaders by country. This is the top 20 only. There is plenty of other companies. The semiconductor industry is still not fully consolidated at all. There is some consolidation. There is a key players in memory or in processor and so on. But you have plenty of other companies, hundreds of companies doing design or sometimes doing smaller foundries or doing a bit of IDM kind of businesses and so on. There is hundreds. So generally, you know, in the industry, most of the key players are already consolidated. You have the 10 key companies for automotive, the 10 key for oil, the 10 key for chemistry, the 10 key companies for pharmaceutical and so on. And the rest is basically negligible. Here, you have plenty of competition on top of the top 20. So, but if you look at the top 20, they are basically within 5 countries. You have Korea, you have Europe, you have America, you have Taiwan, and Japan. So, on 192 countries, it's not so many countries. We may need to have more. I think it would be good. Now, how are they positioned? There is a top 3. The top 3 is the well-known Intel, Samsung, and TSMC that everybody heard about. And you know, their revenue is very high. 79 billion for Intel, 78.5 for Samsung, and TSMC, which is doing only the front end. So their revenue is based only on the silicon and not on the back end and design and so on. Is 50, almost 7 billion. So the average of the top 3 is basically $71 billion revenue in 2021. The others are the memory IDM. They design the memories, particularly the DRAM, the flash memory, and they have very strong revenue and they manufacture themselves everything. So you have SK Hynix and Micron in the range of 35, 30 billion. Then you have the one using silicon foundry almost 100%, which are Qualcomm, Broadcom, NVIDIA, MediaTek, and AMD. So in other words, their revenue here include also, of course, is part of TSMC. In other words, you cannot make double counting. TSMC is mentioned here is not an IDM, but is mentioned because they are so big and so powerful that, you know, just with the silicon, they generate $57 billion. So it's absolutely fantastic. But this revenue is included in the revenue of the others. So either you count the one of Qualcomm, Broadcom, and NVIDIA, or you count the one of TSMC, but not all. And then you have the other IDM, Texas Instruments, Infineon, ST, Toshiba, NXP, Analog Device, Renesas, ON Semiconductor, Microchip, which are between 6 billion to 18 billion at an average of $10 billion. So you can see the huge gap of the top 3 and the remaining last 10 of the top 20. But this is not so critical. Let me show you one chart which is related to the market they are addressing. In fact, most of these companies are addressing different marketplaces. The first market is one, of course, what we call the application requiring ultra high level of speed and integration, which is for applications like cellular phone, PC, TV, decoders, and game. Game is very heavy intensive in graphics and in processor. So the semiconductors that they are selling are memories, micro, modem to communicate, chipset of coming with the modem and the micro processor, the graphic accelerator, and the video decoders. So very high-end device requiring the 12, the 10, the 7, and even the 3 nanometers today. And the one doing so are the one here in blue, Intel, AMD, Broadcom, Qualcomm, and NVIDIA. And you have other market applications still requiring very high level of integration. It doesn't mean that they are doing 100 nanometer, but they are doing much more between the 50 to 22 nanometer. But also required to integrate because it's addressing also the automotive, the industrial market, and so on, a combination of digital, analog, and power. In fact, at the beginning, I talked mostly about the digital part, but I was mentioning that there is analog and power, and companies like ST, Infineon, and NXP, and so on, can combine inside the same chip, both analog part, power part, and digital part, to make one key function for automotive, for industrial, and so on. So the difference is that this requires a very strong understanding of the application. This one, the application is very well known, and generally they have standard product to address it. The one processor for a PC, processor for TV, or decoder for your set-top box, and so on. And what are they addressing? They are addressing the automotive, the industrial, the computer peripherals, the consumers, the IoT, and the medical. So very different marketplace than this one. The products are mostly microcontrollers, huge amount to control many things. The sensors, the power and energy management, the embedded processing, there is still some processor, of course, and the power discrete to activate a very high level of energy, 600 volt, 1000 even volt, whatever. So these are the company addressing it. So you can see 45% of the total market, which is more than $500 billion, 55 is addressed by these players, 45% is addressed by these players. And they don't compete too much. Of course, the one here try to come a little bit here, the one here try to come also here, but you know, the difference is between standard product and specific product. So here you need the technology and the speed. Here you need the understanding of the key application. And this is very difficult to duplicate. You know, moving from computer to automotive, most of the company didn't succeed. They will try, and they are trying, and they are still continuing to try. But you know, the one performing here has been doing that for 35 years. That's a big difference. So, in other words, the split between the two that I was showing before here looks big, but they are competing in parallel. And they are addressing different markets with different products. And they are investing also a lot. You know, people, there is information every day in the press of Intel, of Samsung and TSMC investing tens of billions of dollars. But this one invests tens of billions of dollars also, not tens, but billions of dollars to develop also capacity, R&D, and so on. So it's a kind of two-way market developing in parallel, with, of course, sometimes a few competition here and there. But the core of their business is here for this one. The core of the business is here for this one. And what are the challenges? I have one chart missing still in my presentation, which is one on R&D. R&D is requiring a huge amount of manpower, of good engineers and PhD and masters and so on. But, and also required a lot of investment for pilot line. And pilot line may be a very, let's say, significant amount of investment even before going to the full manufacturing. So I haven't done the chart yet because it's quite complex to differentiate between what is done in R&D for the cost of human resources and the one for pilot line, depending on the machine and the amount of wafers that you want to do in your pilot line and so on. It's a bit difficult to assess, but I will do it. What is true is that, at least from a pure manufacturing standpoint, there was a lot of changes. This is the evolution, from the 1950s to the year 2020. It started by first transistor and discrete semiconductor, very simple device in some way, even if sometimes very high power. The first integrated circuit and so on, and later on, everything concerning microcontrollers, NPU, memories, and so on. In the 1955-60, the fab was basically in the range. It's difficult to assess. I have been looking for days and days on trying to evaluate the cost of manufacturing facility at the time. It's difficult to find, but it was in the range of a few $1 million, which is basically $20 million with the dollars of today. And today, the state-of-the-art one is basically 20 billion. So we went from 20 million to 20 billion in less than 65 years. That's a tremendous amount of capital requirement, which is a challenge of the semiconductor industry. And of course, it didn't go that way easily. At the time, it was even 1-inch wafer, then 2 10-inch wafer, 4 and 5-inch, 6-inch wafer, 8-inch, 12-inch. And obviously, prices were starting to come 100 million, 500, 1 billion in the year 1990, 3.5. And today, the average fab in 12-inch is in the range of 5 to 10 billion. You may have seen an announcement very recently of fab, 4 billion, 5 billion, 6 billion, and so on. And for the typical semiconductor fab, and of course, the most advanced one, between 10 and 3 nanometers, the last one of TSMC was exactly, according to the V Economist, if I remember the page, it was mentioning $19.6 billion, exactly. So this is huge amount of money. Who has fabs of 20 billion in the world? Yes, TSMC. Yes. No, but who has fab, not in semiconductor, costing 20 billion. Even manufacturing, for automotive, for aircraft, for even nuclear energy, for whatever, are a few billion. 20 billion is an astronomical price today, but will be necessary for the coming decades. So this is a real challenge. And the second challenge is that semiconductor has been finally, after the last 2 years, recognized as really at the core of many of the industry. In fact, you have seen in the newspapers, every day, even on TV, that it looks like the lack of semiconductor was at the origin of delivery, supply chain problem, and so on, for almost all the industries. So It is indeed, for us, it's not new, but it is new for the public. But this industry is strategic. It's the intelligent steel of the 21st century. It is extremely competitive. It is extremely capital intensive, but it is at the core of all of them. This supports all the electronic industry. This supports most of the process manufacturing, and also all the service providers, the one using your PCs, the data centers, and everything, let's say, around them. You know, the Amazon and the WhatsApp and so on, and Facebook are using semiconductor data centers. So it is critical, and this industry is reaching 553 billion in 2021. It is forecasted by that 2030, it will be basically 1 trillion, 1,000 billion of dollars, which will make this industry even much more visible, but even much more critical, if not vital, for many other industries in the world. And indeed, you know, Wall Street, in fact, I have taken this chart from The Economist. I made my own chart here based on their chart. But, you know, semiconductor market cap of the company listed on the New York Stock Exchange and the NASDAQ was basically quite stable in the last 10 years from 2005 to 2015, around 800, 900 billion, 1 trillion. And suddenly, by 15, to 2021, it was multiplied by 4.5. 4.5 points times in less than 5 years. And the market, in fact, which was quite stable at the time, is now increasing a lot. And in fact, 2021 will be a 25.6% growth. And 2022 is supposed also to be a very strong growth versus 2021. So this shows that indeed the financial market has been already taken into account the strategic importance of the semiconductor business and industry. And if you look at electronic and semiconductor, indeed, whatever it is in research program, whatever it is in development and innovation program, whatever it is in the infrastructure program, semiconductor is at the core of it. And this is unique. So, to summarize on a more even visible way, you know, if you take, let's assume that this is Singapore, you know, you have everything, traffic management, air pollution, smart parking. You remember that you have the car on in your car with a chip on it. The one of smart water management, smart energy management, electrical vehicle charging, and so on, smart lighting with LED and many things. Everything is becoming, you are surrounded by semiconductor in your life, in your activity, and it is something that should be now more visible to both the industry and the public. So, if I can summarize the key takeaway, it's not really takeaway, but some messages that I would like to pass. The first one is semiconductor industry is at the core of almost all of the industry sectors and services in the world, and its pervasiveness looks unlimited. Now it's go to medical, it go to robotics, it go to to green energy, to everywhere. With its incredible high level of innovation, the semiconductor industry will continue to provide huge opportunity of employment. You can do a real career. I know that sometimes the word looks a little bit strange for the young generation, but you can do a very strong career in semiconductor. There is plenty of requirement, not only of workers, technicians, and engineers, but also of people from the business community, students, for everything, for sales, marketing, for accounting, for audit, for procurement, for treasury, for everything. And there is a very strong requirement of individuals, in all the key countries in particular I was mentioning, in Europe, in US, in Singapore, in Korea, in Taiwan, and so on. They are all looking sometimes desperately to find the resources to follow the capacity investment that they need to put in place. We have seen that in Singapore there is plenty of new fab arriving. We'll discuss that maybe later on in the Q&A, but there is plenty of requirement of HR, manpower. And the last one is maybe also a message in this case to most of the companies, saying non-high-tech companies, the one in insurance, the one in the banks, the one in everything, in construction. The construction of new building requires a lot of semiconductor. They have to take care of the management, the energy management of the solar panel, the windmills, the elevator consumption, the security, everything, the connectivity of the building and so on. So you have people working in construction doing really smart building and working, in fact, on electronic and semiconductor inside. So the construction business, which was never using a semiconductor 25 years ago, is starting to use a lot of semiconductors themselves. The insurance, they have to assess the risk with the semiconductors. The banks, they have to look at M&As, they have to look at financing huge amount of, let's say, this industry. And the better they know about it, the best it is for them. So the non-high-tech company should start to look for knowledge and resources related to electronic and semiconductor within the coming years to get prepared for their long-term plan of development for the next 5, 10, 15 years. And that concludes my presentation today. Thank you very much.
Okay, thanks for all of you who are still with us in this room or online. We're going to have a small panel. We're going to discuss about 3 questions before we open the floor to answer questions from both in this room and online. I'm Li Yan. I'm professor of digital transformation at ESSEC Business School. And Francois, Stanley, you want to introduce yourself?
Okay, short introduction. Myself, I'm also in the semiconductor for more than 20 years. Started, of course, obviously with HP 6-inch. And currently I'm now an EMBA student in ESSEC.
Okay, so we're going to start with the first question. So actually, global chip shortage since 2020 has exposed the TSMC and the Taiwan semiconductor manufacturing companies' critical position in the global semiconductor supply chain. So as Francois mentioned, as most of you know, TSMC currently is the largest chip maker in the world with 53% of market share, together with 3 other smaller Taiwanese players like UMC, PSMC, and VRS. Taiwan's chip making actually accounted for 63.3% globally. Actually, and TSMC, as Francois mentioned just now, currently the market capitalization ranked the 8th in the world. Actually, could you please explain to our audience what factor contributed to Taiwanese semiconductor ecosystem, which determines their current dominance?
Well, I was living in Taiwan for a few years, so I have a bit of experience also on the field in Taiwan. It was in the 1989, 1991. By the way, it was a good time for the semiconductor and the economy of Taiwan at the time. But Taiwan was having already, as I mentioned a bit in my presentation, a huge experience on high-tech manufacturing for electronic toys, for PC already in the 1960s, 70s. And also the country policy was really to move to high-tech because Taiwan has no natural resources. Taiwan has no oil, no, let's say, copper, gas, gold, diamonds, or whatever that you can find in some country in the world. So, and a very limited agricultural capability and space due to the mountains in Singapore. So if you want to go to compete in the world, they found that indeed high-tech will be for them the way to do it, on the brain and the ability to develop the high-tech industry from Taiwan. So in the 1980s and 1990s, what they did is to repatriate a huge number of key engineers, experienced Taiwanese engineers and managers from California, from Silicon Valley, and they wanted to start Hsinchu. Therefore, they attracted as much as possible from E3 and ERSO and with Hsinchu and so on, and the companies operating there, a strong attraction to really have Taiwanese coming back to Taiwan. And a lot did. Then there was this government agency I talk about, E3 and ERSO. And E3 and ERSO was, at the time in the 1989, 1990, the president was Mr. Maurice Chang himself. He was hired by the government to be the one making the strategy of electronics and semiconductor in Taiwan. And therefore, later on became the founder of TSMC and the success of this company. So then there was this vision of the technology park. You know, the Taiwanese have already learned very well that there was two ways to win. First of all, the technology, they were close to Intel because they were doing the PC motherboard and then the PC. And they realized, you know, that the leadership and the strong also position of Intel was coming from where? The leadership in the technology. And therefore, they started to really put a lot of effort in R&D. And also they saw that, you know, Silicon Valley was a place that was really making the innovation mushrooming from all over the world, for all over the world. And therefore they started Hsinchu. Hsinchu was also a mix of electronics, semiconductor, hardware and software company, R&D laboratories that even later on started to look at many other applications in graphics, in cellular phone, in communication, in medical and so on today. And at the end of the 1990s, indeed, they have this vision of moving Silicon Foundry to the leadership position. At the beginning, TSMC was very good in manufacturing. Most of the Taiwanese companies were excellent in manufacturing. But they realized, you know, that it's not good enough. You need to have an international customer base, having an international marketing to attract the key customers worldwide, and to have also a very competitive R&D level. So in the 1990s and year 2000s, they started really to focus on international marketing and R&D. And all combined, you know, that has been making Taiwan extremely successful with the today result of TSMC, but UMC, MediaTek, and many other smaller companies, or in other devices. Taiwan is also a leader for manufacturing with Foxconn, with Delta, in power supply. There is plenty of leaders in Taiwan on top of the semiconductor one. So Taiwan indeed has been making the high tech at the core of their development and has been extremely successful.
I think it's also in early days they decided to give up chip design, only focus on chip manufacturing, right?
Yes, they feel that, you know, in fact, at the beginning, Taiwan was very good in manufacturing already, as I say, for many other electronic devices, the toy, the PC motherboard, and the PC itself. And they were feeling, you know, that manufacturing is their cup of tea. They are excellent for them in terms of cost, discipline, yield, quality, everything, discipline and so on. So they started with that. But then they realized that you have to be leader in the technology if you want to compete, and that you need to grab the key customers worldwide, not to have the one close to you, only in Taiwan or very close to Taiwan. So they did so, and they became extremely successful with that.
Actually, may I just add on, and what actually feel that that grow for for Taiwan is also because a lot of companies decide to go fabless, and they need somebody to actually manufacture the chips for them. And that's how I think Mr. Maurice Chang being very entrepreneur, caught hold of this, and just.
I think he knows that this this is an unusual model. Very few industries have such ability to separate the different manufacturing steps.
Yeah.
People doing automotive do the automotive. You don't buy, an engine somewhere, the body somewhere else, and the electronics somewhere else. You do the car.
Yes.
So here you have a model where you can do you can be extremely successful just doing design, like NVIDIA, like MediaTek, like Broadcom, Qualcomm, or EMD. And then you can be also very successful in backend. There is plenty of backend operation in Malaysia, from Malacca to Penang, which are extremely successful manufacturing for backend operation. And then you have the one of front end, which can be done by the IDM themselves or by the silicon foundry. But this landscape of the business model is very unusual to remain like that today.
Yeah.
So that's
The factors contributing to it.
yes. I think that I can comment on TSMC, but it's true that the chairman and CEO has been having the vision that this silicon foundry business model can work strongly and become the supplier of silicon to the key design house worldwide. Yeah.
Okay, so face this dominance of Taiwan chip maker, governments and also industry players worldwide, they currently are trying to diversify away from Taiwanese chip makers through several potential non-Taiwanese sources. For example, China. March 2021, last year, China government unveiled its 14th 5-year plan, because every 5 years we are going to have a 5-year plan. So in this 5-year plan, it emphasized on China's technological ambition and desire to be more self-reliant, especially on chip making. So to reduce the reliance on US and Taiwanese imports amid the current tension between China and the US. So for example, SMIC, China's largest chip maker, so they announced last March, $2.35 billion new chip plant in Shenzhen. And half year later, in September, they announced another $8.87 billion chip factory in the outskirts of Shanghai. Similarly, in US, Intel announced about $20 billion investment in chip making, and in Korea it's even huge. They announced last May they announced $451 billion plan. Yeah, so this is from a lot of companies, and among this, 151 billion were from Samsung. So look at all these efforts from China, from US, from South Korea. To what extent do you think we can diversify away from Taiwanese chip makers?
You already given a good part of the answer, but let me maybe summarize from a global perspective. You have, I think that the trend is improving on the diversification. First of all, Samsung is continually, as you say, increasing its capacity and allocating a more significant part even of their capacity, more and more, gradually, to silicon foundry business for the design houses. Intel has announced since March 2021 that they will do also silicon foundry. This is a big revolution. Intel has been a standalone supplier in a very strong position on processes for the last 40 years and was not doing at all any silicon foundry. So it's a big revolution of having Intel starting to say, I'm going now to do silicon foundry for the other key design houses. And they did it very quickly. In fact, recently they have announced the acquisition of Semiconductor in Israel for $5.4 billion. So increasing their own capacity. And they will do also some new fabs, 2 new fabs, in fact, in Arizona. And I am sure that they will allocate more and more even of their internal capacity to silicon foundry capabilities. So acquisition and internal capacity from Intel will be also a key addition to the silicon foundry diversification. Then you have other silicon foundries. You mentioned a few of them, including SPIN, but let's not focus only on the Chinese one. All of them are increasing capacity in Singapore, in particular Global Foundries. Global Foundries in Singapore is a fab that will be in production by 2023.
4 billion.
It's a 4 billion investment. And UMC has announced a 5 billion investment for a fab in 2024-25. Also IDM, like Texas Instruments, like ST, Infineon, and so on, they're also very significantly increasing their capacity. Now, it's not with tens of billions of dollars, but with billions of dollars. But all of them are drastically increasing their investment to increase capacity in Europe, in Singapore, in front end, in back end, and so on. Then you have even TSMC itself. TSMC itself is doing things outside Taiwan. TSMC has been already announcing a manufacturing in Phoenix for $12 billion in Phoenix, in Arizona. And they have also announced recently a fab in Japan with a $7 billion investment in cooperation with Sony to really also address the Japanese market, which has also a strong requirement of most of the key electronics players in Japan. And China will do later, I'm sure, you mentioned SMIC and so on. But today is a little bit limited by, of course, the US restriction on using US technology, including on manufacturing equipment. And this may be a little bit of a concern for them to drastically increase capacity on the high-end part of the semiconductor plants. So you can see there is plenty of things that you can do to diversify with Samsung, with Intel, with other silicon foundry, with other IDM, with TSMC itself outside its country of origin, and obviously with China, I'm sure later on.
Thanks. Stanley?
Well, I mean, I think it's good to diversify because we are actually depending almost 60% on them, you know, and I mean, in time to come, if they become really dominant, then the price will be controlled by them as well. So I think it's a good timing now because of some political issues as well. It's good to start diversifying away, kind of depending on them too much.
But I think it will take time.
It will take time. It will take time. I mean, you need time to develop the capability up as well, especially for China. But of course, supply will be also a challenge because actually not just we are facing the chip shortage, but actually we're also facing equipment shortage. You know, I mean, raw material shortage as well. Yes. So I think it will take a slightly longer path. Sure. Yeah.
It has been already for 2 years already almost, and it will continue in 2022. But we'll see. It will come at a time where the demand will fit the capacity. I'm sure this has happened in the past 60 years and will happen.
And I mean, being in semicon for a long time, it's always like a roller coaster, right?
Sure.
Yeah. Very cyclical. Sure. And the cycle is getting shorter and shorter and shorter.
So 1960 to year 2000 was basically 15% compound average growth rate. But the slide the line is like that. So if you look at it year after year.
Yeah.
Okay, and so if we look at where we are, so actually semiconductor is a key pillar of Singapore's manufacturing sector, and with global players like Global Foundry, also UMC announcing a plan to expand production in Singapore. Do you think Singapore will benefit from so-called shift in supply chain in semiconductor industry? And what is the role Singapore will play in the near future in this industry?
Singapore will have a key role. It has, Singapore has been, as I was mentioning in my presentation, the history, but already very present. It's one of the very unique manufacturing hubs for the semiconductor industry in the world, and they are covering the entire value chain. There is, they cover from the crystal ingots with, for example, Siltronics. We have announced a joint venture with Samsung, a $2 billion investment for creating a new ingot and wafers manufacturing in Singapore. And there is Global Foundry, there is UMC and so on. And Singapore has also the whole ecosystem. In other words, there is all the environment of the people delivering maintenance support, software support, CAD tool support, gas and liquid support, equipment and so on. So, which is of vital, let's say, for becoming successful in this industry. And this requires a long time to have around you the full ecosystem of the semiconductor, which is very expensive, very intensive in terms of requirement of human resources and so on. Around you is something that takes decades, let's say, to put in place. So the model of Singapore cannot be duplicated tomorrow morning in another island, clearly. And in fact, the limitation today may be mostly on HR, where Singapore is not maybe issuing from university and business school enough resources to really fulfill the requirement of all these industries that is so dynamic and energetic to really design and manufacture the product necessary for the economy and the development of the industry, of most of the industries. So the more critical and vital it's become, the HR will become even more also vital and critical.
Yeah, I mean, actually the semiconductor industry for Singapore, I think started as early as
1968.
Yeah, with the first wafer fab being STMicro alone. So I think our semicon journey has come a very, very long way. And, we really have developed the whole ecosystem, and with the higher institution focus on all these science and technology. So definitely we are actually very ready in terms of human capital. So, and it does help to bring the country and also our technology up one level. And it's not easy to duplicate. I think this is really our strong unique selling point for Singapore. I mean, exactly like Taiwan, no resources, no oil.
It should be a combination of local resources and of course some experts coming from all over the world. But we need more and more even local resources.
Yeah. And interestingly, the whole semiconductor industry ecosystem is actually getting more and more integrated and getting more and more smaller. Yeah.
Okay, thanks. So the last question is actually the question my students always ask me whenever we talk about Moore's law. So they said Moore's law is ending because there's a physical limit as how small the transistors can be. So as Francois mentioned, in less than 70 years, the number of transistors on the chip has increased from 1 to 50 billion. Yeah, so actually, if you look at, so for example, I remember some years ago when we already reached 28 nanometer, people will say, Moore's law is ending, cannot get smaller. Yeah. But as you mentioned, IBM's recent breakthrough is only 2 nanometers. So how long do you think Moore's law will continue?
Well, first of all, let me tell you that when I started myself with TI, at 1 micron at the time, they were telling me it's a black hole. We don't know how it will be done below even 1 micron. So we are now almost at 1 nano, and it's still working very well. Now, of course, the equipment and the technology has been doing a lot of innovation and progress. But the Moore law has been basically working very well for the last 55 years. So it was was not a law, it was really, let's say, an empiric law that was done by Moore, was really have the vision that indeed duplicating the complexity, in fact, the number of components could fit on a single chip will double every year. Then he say 1 year and a half and then 2 years finally. And while the cost could be halved, of course. So this law until basically 2020 has been almost working, plus or minus, because there is, in the analog and powers, there is the combination of it takes a little bit more maybe space than the concentration on the digital one. But the specialists are saying, yes, indeed, the limitation could be on the thickness of the gate. And what they call even the gate length, which is not exactly the same, but it is the thickness. Because the thickness is on the silicon, the atom of the silicon are 0.235 nanometer apart. So the gate is basically at 30 atoms thick. And the more you will have to put on the silicon, the smaller you have to reduce the thickness of the gate. And in 8 years, it can be the dimension of 7.5 atoms that you have to reach. So it's something which I am not a specialist, and I will not, let's say, enter too much in detail on that. I leave that to the R&D and the specialist. But obviously, the dimension of the gate and the issue also the wavelength of the laser for the deep UV and extreme UV that is going in the photolithography to do with the masking, let's say, the scheme of the design on the silicon will be also a challenge. The wavelength, the brightness of the light and so on will be also maybe with some potential limitation. But with my experience of the below 1 micron, we don't know what will happen. I'm feeling still a bit comfortable.
Okay. Okay, Stanley?
Well, I think coming from a equipment manufacturer side, I think it's possible. But I mean, we probably will be limited by how much the equipment can do. But I know there's a lot of R&D ongoing. They are trying to push the limit of the equipment, right down to even the sub 1 level. I mean, these are kind of very, very sensitive things that we cannot share openly, but I think it's possible.
Everybody is working on, they have been working on 100 nanometer, on 50 nanometer, on 24 nanometer, on 10 nanometer, on 3 nanometer.
2 nanometer.
Yeah, it still works. And even the 2 nanometer of EBM is done with regular, let's say, technology, very advanced, but regular one. So we'll see.
And this 2 millimeter technology is not something yesterday. They have been doing for the last. So I'm sure as we speak now, they are even pushing to 1 and below.
Yes, yeah. But this is what is fascinating, this industry. You never get bored 1 minute in this industry. There is so much competition and innovation. I can tell you, I have never been, let's say, getting a little bit. Sometimes you can be a little bit tired, but never bored in this industry. I can, when I was hiring people, I say, I don't know what will be your career. I cannot guarantee you anything, but I can guarantee you one thing: you will never get bored in this industry.
Okay, thanks a lot for the sharing. I personally learned a lot. I hope everybody feels the same. So, any questions from the audience?
We'll start with any questions from the audience first. So please just raise out your hand if you have a question.
That's one question. So firstly, thank you so much for the insights with the comprehensive sharing. So you mentioned that how this industry is cyclical, the growth curve just like a roller coaster, because there is always a lag between the supply and demand. It takes several years to build plants and they catch up with the supply. But do you see, for example, the industrial 4.0 and the implication of this technology like blockchain and digitalization may perhaps help these companies to better manage the orders and reduce the cyclicity of
There is plenty of things that can be done to avoid this huge, say, ups and downs. I remember in 2000, the market did plus 38%, the year after it did minus 28%. So in 2001, which was the explosion of the high-tech bubble. The issue is you can do a lot on the supply chain, you can do a lot on the interface between customers and suppliers and partners and supplying of equipment and so on. In fact, it's a whole ecosystem that has to work together, and they are doing it more and more. The only structural difference is due to the cycle time of increasing manufacturing. The one generally of our customers, from the simple one doing coffee machine to the highest one doing the aircraft, is generally they can, but the consumer, not forget aircraft for the moment, but on the consumer side, they can increase capacity in 6, 9, or 12 months. In some, and they can even create almost a new fab. The building is not a clean room, that costs almost $1 billion. The amount of investment is not in $billions, but in hundreds of millions. So decision, process of developing the solution and making it effective can be between 9 months even to 18 months. So one of semiconductor, because of the highly capital-intensive decision, you have to decide if you put 5 or 10 billion. You have to find the equipment supply, which is also sometimes difficult. You have to set up the clean room, which should avoid any vibration and be clean defect density at a very high level and so on, which costs already hundreds of millions, if not $billions of dollars. And then to set up the equipment to not only setting it up, but to reach also the yield and the manufacturing efficiencies that you need to be competitive on the product. This takes 2.5 years. So this difference of basic cycle time of the two industries, generally is one of our customers and the one of the semiconductor itself, based in particular on the supply of equipment and so on, which is already extremely complicated and costly, makes the things always a little bit difficult to adapt. But it will happen more and more that, in the supply chain, in the visibility that customer can give to the supplier, in the way of operating the supply chain, in the way of managing inventory on all sides of the ecosystem, from the customer to the supplier of equipment and so on. But you cannot, you cannot have, inventory of photomasking, let's say photolithography at the price that they have. If it's 50 million or 150 million, it's a huge investment just for one machine. So it will improve, but the structural difference of cycle time of generally the end customer and the semiconductor makes the things a little bit difficult to adapt. And I have seen that for the last 40 years. But we can improve, I'm sure.
Actually, we are constantly learning, learning the trend and the pattern to improve. But I think one thing good about, being cyclical is there's always new things to look forward to, new technology,
Sure.
Yeah.
Question.
Thank you so much. Thank you for having us tonight. So I have a question from a more geopolitical point of view. So Western sanctions against Russia have already...
I stop you. I will not answer geopolitical question. It's too emotional and too politics, and I am not, let's say, in that position. So I will not.
Yeah, you can reposition your question.
Yeah, no, you can pose a question, but I will not answer because it's too emotional and political, and I am not in a position to take a position on that kind of question.
Absolutely. So Western sanctions against Russia have already included a ban on the sale of semiconductors. So would you qualify the semiconductor industry as strategic? And do you think states should stockpile semiconductors or similar technologies to remain competitive in the future?
I will not comment on that. The geopolitical is bringing a factor which is beyond the rationale of this industry, which is working very well worldwide. This is an industry which is in fact global since the beginning. Even in the 1950s, it was global between US, Europe, Japan, later on Asia, and so on. You have seen in my presentation, and it will work very well like that. Now, if a country wants to play the independence, and which is true, which is good, but wants to have, monopoly or put, let's say, pressure on other countries and so on, that's a different story.
Stanley?
Sorry, sir. I mean, I totally agree. I mean, it's a bit sensitive at this point in time, but we do know that, to process the technology, I think is every country's, roadmap. Right? And,
I can maybe say something on the future. What I think is that I will be happy to see other continents or big country also, let's say, starting to appear on the landscape. India, for example, deserves to be on the landscape of semiconductor. In fact, they have a program. The Prime Minister recently said that he will invest 17 billion and so on, but there have been a lot of announcements, and for the moment, there is still no real semiconductor industry in India. But they deserve to have this industry and to play a role also. And I hope that they will appear, let's say. But the barrier of entry are more and more difficult. 40 years ago, it was not as costly and as difficult to enter. Today, even if you put the money, you have to get the experience, you have to get the understanding of the application, the experience on the technology, the knowledge of the ecosystem and the customer base worldwide and so on. It's more and more difficult to enter. But Latin America, or as I mentioned, or ASEAN is already quite big because there is Singapore basically on front end, and Philippines and Malaysia has a huge network of backend operation. So it's working very well, but there is still no leaders from that part, and maybe some leaders could appear in the future, particularly in backend, which is becoming more and more capital intensive. It was much less than front end, but it's becoming now quite significant. So I expect that for the sake of diversity of supply, of region of origin, of independence of some key countries, some players will appear in the coming 10, 15, 20 years, not tomorrow.
Yeah, I think based on Francois' presentation, you can see semiconductor industry, the value chain is one of the most complicated among all industry, and it really needs a global collaboration. So I'm a Chinese, so I personally feel that ever since the trade war between China and the United States, for example, Huawei, our high-end smartphone, the market share in our own country dropped from 23% to 7% from last year to this year. Why? Because ever since the trade war between China and the US, a lot of Chinese people will opt for Huawei instead of Apple because we want to support our own brand. However, currently, because we don't have the high-end chip needed for the high-end Huawei phone, we have the demand, but there's no supply. They cannot manufacture. And also, as Francois mentioned, the photolithography, this very complicated process, which is currently dominated by ASML, a Dutch company. Yeah, currently China don't have the technology. Yeah, so I completely agree with you. For the healthy development of semiconductor industry, yeah, let's wish for a peace world.
Yeah, I mean, maybe we change a bit of perspective. Hopefully, semiconductor will be marrying all the countries with different strengths together, and then we coexist. I mean, you are good at back end, I'm good in front end.
Yeah, more rational way.
Yeah.
Not the currently very mad way.
Good question.
Yeah. So thank you for your presentation. You mentioned that the semiconductor market is going to grow tremendously the next 10 years. Do you think this growth will favor more the already big existing corporations, or it will favor more the small and medium enterprises and the smaller companies, especially in Singapore?
No, it will be both.
Both?
In fact, indeed, the market, the IDM, the market has been increased worldwide 25.6% this year, from 440 to 550, basically $1 billion. And it has been for both parties. So the IDM, the one of Texas Instruments, Infineon, ST, and so on, has been increasing also by 25, if not more, let's say, in their market, the one that I was showing, as the others did. Some may particularly increase maybe more, 40% in some cases, but the two markets are growing also anyway. There is not, one market that will continue to grow 40% and the others that will be stagnant. So with sometimes a bit of differential, but all this market, the automotive market is still, as you can see, increasing a lot. The pervasiveness inside the semiconductor makes this market growing a lot. So they are not independent, but they are really having their own growth in parallel again. And as I say, the people addressing the second market, not the high-end, very high-end one, are, let's say, doing it the same way. They are increasing their capacity, doing investment, developing application and so on, like those. Now, the journalist, has a tendency to talk a lot about the benefits. It's a very visible one. The others are working also a lot and developing very well.
Okay, thank you.
Okay.
Thank you. Any other questions from our attendees in campus?
Maybe just, we have been talking about inorganic semiconductors. What are the perspectives for organic semiconductors from your opinion? Because they have different functionalities and can answer different applications.
Yeah.
Like OLED or OPD. Yeah, what about?
Well, I may not be so knowledgeable on that. I can say that a lot of other technology, like silicon carbide, like gallium arsenide, are becoming more and more powerful to improve the speed, integration, and so on. I will not be able to comment on the organic one, even if I know that there is progress, but I am not a specialist of it. So I will avoid to, let's say, do something which I'm not so knowledgeable.
Thank you for your presentation. You mentioned that Latin America could be a potential player. May I know what made you think like that? And is there any, maybe starting players in Latin America?
No, there is not. Like in India, there is no particular players, and it's even much complicated than in India because there is many states in Latin America. But the Mercosur is also one way to unify a bit the economy and the industry. What I'm saying is that in principle, they represent a continent per se, and let's say having 550 million people, including Mexico, and deserve maybe to look at it seriously in the coming decades. But today, they have not been showing a lot of willing to invest in that area. India has been already showing a few times. They didn't succeed, but you can feel India has already the software knowledge. They are making progress on the hardware by dealing with customers and so on and suppliers. And I have seen many times myself when I was taking care of Asia, there was India in my perimeter. I have seen the willingness of government and companies and industry association to develop an industry in semiconductor. I have not felt the same when I was in charge of emerging market from Latin America. There was some countries that was showing some interest, but as of today, there was no, they were still working on infrastructure and many other areas on energy and so on, and industry, not in the semiconductor one. Electronics also, you know, they are doing a few already of electronics themselves, in TV, in some application and so on, in power supply, but it's quite limited. They are still purchasing a lot from China, like many other countries are doing it. So, but I will encourage such continent, we say, to really have a strategy of developing their own industry. It is something that will be good for them and for the overall choice of potential partners for the key players. The more they are, the better it is anyway.
Thank you.
Any other questions from our attendees in campus? If not, we'll move forward to the questions that we have actually for our attendees online. I'll first actually start off with a question specifically for Francois. Why is the competitive edge of the top 3 European players, STM, NXP, Infineon, especially in the automotive semiconductor? Do you think they will sustain the worldwide competition?
In the market, for sure, they have been doing in the last 35 years that I have been myself and involved, and they have all the ingredients to succeed. In fact, they have, as I was mentioning, there is a deep, not only knowledge of the technology, but also on specific technology like analog power, combination of analog power and digital, which most of the other players doesn't do. And they have, in particular, a huge experience on understanding the application, which, you know, in the world is in some way naturally analog. So at a certain point of time, you have to convert it, and you have also to drive equipment. So the combination of analog power and digital is key. Of course, for a PC, not so much. You need to have computers, let's say computation. But, you know, in many applications, like in fact sensors, you need to have, it's a bit analog to do an injection, you know, for an automotive engine is also analog at the beginning. You have an engine. An engine is an analog, let's say, part, and so now it's more and more digital because it's let's say electrical car. But all these companies that was mentioned are all doing very well. They are extremely profitable, generating cash and giving high growth of revenue, and they have barrier of entry which are very high. And therefore, I'm sure that they can continue to address this market and to develop many other applications, as I was mentioning, in IoT, in medical, and so on. There is plenty of new applications.
Thank you, Francois. The next question is also addressed to you as well. Next question is, there is no Chinese name among the top 20. What are the chances of China to become a competitive manufacturing center in the advanced nodes below 40 nanometer? Are the restrictions on water fed equipment a big obstacle?
Yeah. It can happen. There is, you know, the government, as was mentioned by Professor, was mentioning, you know, that 50 or 100 billion, you know, will be put on the table to help development of in-house manufacturing, silicon foundry, IDM, and so on and so on. And they can, let's say, fight for it. The competition is tough because those are already well entrenched. They have themselves also the ecosystem on the equipment, the suppliers, the software, the application, and so on. You know, China started just in the year 2000, basically, a bit earlier for some of the players, but the real development was there. They have a very strong driver because they do a lot of the manufacturing of the electronics. So why not? But you know, the top 20 are already well entrenched since a long time. In fact, I can tell you, Intel is in the top one since almost 40 years. It's very, because they have been the king of the processor for the PC and so on. But a lot of the players here, but you know, new players, Samsung or TSMC 25 years ago was not in that ranking at all. as I was mentioning, in 1985, when I was in the US, in the top 5, we were having 4 Japanese companies. Now you have only 2. So the landscape will be changing. As I say, there is plenty of competition, but the barrier of entry both on investment, manufacturing, R&D, and understanding of the application experience of the market and so on is becoming more and more difficult to compete.
Thank you, Francois. So now the next few questions is actually addressed to all speakers. First question is, what are the breakthrough innovations and initiatives taken by the semiconductor manufacturers to reduce the carbon footprint and environmental impacts?
Could you mention green?
Sorry.
Green technology.
Well, I can say a few things, but it's of course they are doing new things every year, and I'm not anymore, let's say, on top of it because I'm not anymore in the semiconductor energy and growth of today. But semiconductor has been trying to be a very clean industry as much as possible. They are using a lot of water, a lot of power, but the water is largely recycled. They are making, putting even reforesting, a lot of land to be sure that, carbon emission is absorbed. They are making equipment to be having the less possible consumption, whenever in action or even in standby and so on. They are participating to make the world less consuming on every application, on driving the solar cell and the panel. And the solar cell panel was a key issue. You have to extract the value of the panel when there is dust on it, when there is when one part of the panel is broken. At the beginning, the entire, let's say, panel was basically not working at all. Now, there is microcalculator for each cell to be sure that you can, absorb still the energy, even if one doesn't work, if one has been having some dust on it or has been, there is a leaf, let's say, falling on the solar panel, the rest of the panel is working. So plenty of electronics and of power and controllers has been put at the service of the panel to make it extremely efficient. So the entire, in fact, electronic industry is really trying to work itself to be less and less consuming and requiring less and less power and making it less and more clean by particularly on the water that it's recycling very well, and also building things which are going to be extremely low power consumption, green energy, harvesting. The smart metering is to have you consuming less energy, and this is done because we have a very smart way of measuring the consumption, of informing, of making your system working during the night where there is less demand than in the day and so on. So everything is done to do so. Since the beginning, not since 5 years because it's fashionable, since 30 years.
Professor Yen, anything to add?
I mean, at our our equipment manufacturer level, we're also trying to reduce all these emissions and stuff like that. But I just like to kind of share a bit, like there's certain materials that we can't replace.
Sure.
And as technology gets more and more advanced, in fact, these special materials is, you require more and more special metal, rare metal. So this is part which we are still trying to actually, see how we can replace it in order to kind of reduce. Yeah. But sometimes we can't be helped, right? I mean, we really need special.
The bonding, for example, for the packaging and so on, was done with gold at the beginning. Then it has been done with copper. I understood that now it can be done even with aluminium. But at the beginning, you needed the ability of the gold, to be a real conductor, to have the perfect, less default than any other. And then progressively we went to the copper and so on. So we are using less of the easy to find, let's say, resources and so on. Yeah. So, because copper and aluminum are much easier to find in cost. So this industry has been deeply working on being internally and externally providing solution to be, in fact, as much as possible, clean and safe.
Well, the final question that we actually have is for all is, could mergers and acquisition activities happen for the top players to close the technology gaps between target markets?
There is always a huge amount of merger and acquisition in semiconductors since also 50 years. Now, some area has been a little bit consolidated. For example, in power device or in memories. Now there is a few key players, and it's difficult after that to enter in this business. But since there is a lot of medium and smaller companies, when I say medium companies, that can be, you have seen the top 20 are basically still at least above 6 billion. So there is plenty of companies doing 2 billion, 1 billion, 500 million, or 100 million, and they're doing very well. So between them, I'm sure that there will be still a lot of consolidation of acquisition. They need the software, they need the access to the knowledge of some specific area and so on. So the M&A, the bankers has to, I'm sure, a lot of things to do in M&A for the coming years. And in the consolidation at the top level, we'll see. But some of them are now, let's say, most of them are big companies. So, and they have their specificity, their origin, their way of operating and so on. So consolidation should be done when it brings synergy and complementarity. When SGS and Thomson merged, there was a lot of synergies and complementarity in terms of location, in terms of product line, in terms of manufacturing, in terms of everything, So it has been a very successful merger of equals.
Yeah, so I think there's also a lot of regulation issues. I think if you follow the news recently, NVIDIA just together with the SoftBank, they announced the termination of the acquisition of ARM. And people said, actually, before that, a lot of people said there's a lot of reasons why NVIDIA and ARM should be combined, but there is also a lot of reasons why it shouldn't. Yeah.
Because ARM has been
the standard.
Mentioning that has been a reference even.
Yeah.
There was other reference platform for microcontrollers in particular, using the core of ARM as a reference for the process of developing a full microcontroller. And a lot of people, it was an open access. You're forced to make the necessary cost of investment to access this database and IP and so on. But most of the company were able to do it. If you reduce it to one owner, it's a big of a problem for many users. And I can understand that this has been scrutinized by the regulators.
Stanley, anything to add?
Well, I mean, not actually just on the device manufacturer side that there's some mergers and stuff. I mean, over at our equipment supplier side, I'm sure you heard of many M&A along the way. And actually we are also left with kind of like a few major players.
Sure.
Yeah, and if you can recall, I think a few years back, Applied and Tokyo Electron almost kind of have a merger. But what Prof. Yen says is quite true. I mean, somehow you still have regulations to control it.
Yeah. It's good. The regulators are there for them.
Otherwise, you'll be end up like having one big cheap company and one big.
Exactly.
I think the ecosystem will not be very balanced.
Yeah.
Diversity is key.
Yeah, diversity.
On every side.
Well, on this note, we come to the end of the Q&A session. To our attendees online, kindly unmute your mics. Let's actually now, for all our attendees, please give our speakers a big round of applause to show. Thank you very much, everyone, and goodbye for now. Thank you.
Thank you.
Thank you very much.